Hello everyone. There is a white void behind me because we are in my bathroom, and it's kind of weird place to start the video, but there is a good reason for it. I wanted to show you something. I was at the grocery store the other day and I got one of these teeth whitening kits that you find on the pharmacy or the grocery store, pretty common, and I thought I wanted to make a video about them, explain some of the chemistry and physics that goes behind something like this. And the thing that I like about this is that it's not just the little gel that you're supposed to put on your teeth, that it's, at least in theory, it's supposed to make your teeth whiter. You kind of put it on, and then what you do is you grab one of these light things and then you put it on your teeth, and then the light is supposed to somehow interact with the gel that you put on your teeth, and that is supposed to do something. Well, what is it supposed to do? And that's what I want to talk to you about today. But let's not do it here in my bathroom. I just recorded this for a bit. That bit is over, so let's go somewhere nicer to talk about how this works in terms of chemistry and physics and all that good stuff. Okay, so this is a much better place to talk about science. I even got a blackboard. That's pretty nice, right? Okay, anyway, so before I talk about the kind of the chemical reaction that is going on in the teeth whitening kit, I just kind of have to talk to clarify a little bit what kind of assumptions I'm making here. Ideally, I would like to make the video accessible to everyone, but that's kind of impossible, right? I have to make some assumptions. I think in all of this explanation that I'm going to attempt to do, I'm going to assume that you have at least taken some kind of chemistry class. If it's an introductory college class or even a high school class, I think you could probably follow what I will talk about. And if something is not clear, feel free to ask a question in the comments. And the other thing, I guess it's not going to be a super rigorous explanation, right? I'm going to hand wave a bunch of things. I'm going to try to make it accessible, so it should be okay. But you never know. Like sometimes you can get into the weeds of things, and things become more complicated than you intend to. But hopefully it doesn't get too complicated, and hopefully I don't make too many mistakes. Who knows? All right. So we want to talk about sort of how does the teeth whitening kit work? You put it on your teeth, you put the light in, something happens, it's supposed to whiten your teeth. I don't know how well it works, but at least that's the theory anyway. And we know that inside the teeth whitening kit, there is some kind of, hydrogen peroxide, some kind of peroxide reaction, and that's what we're trying to understand. So how do I understand reaction in terms of energetic? Let's draw in the blackboard what is known as a reaction coordinate diagram, and then I'll explain what that is after I've drawn it. Well, like any good graph, we should probably label what this is. So this is what is known as a reaction coordinate diagram, and it sort of depicts energetically how we go from the reactant side to the product. So let's say we have a reaction going from A to B, right? And this is A and this is B, and we're going through some kind of, coordinate system, and this is the energy of the reactant. This is what is known as the activation energy, and this is the energy of the product. And let's kind of label the axis, right? So we have the y-axis is the energy. That's pretty self-explanatory, right? The x-axis is the reaction coordinate. This is a harder concept to explain. It's a harder concept to grasp. It's abstract. It's a bit vague. It kind of represents a collective variable of all the atomic multidimensional coordinates of all the motion of the atoms as the reaction proceeds. So this is best illustrated by an example. So let's consider, if you've taken a chemistry class, you probably have talked about what is an Sn2 reaction. You have sort of an OH group that comes in and binds to this carbon group, and at the same time this bond between this carbon and this bromine is broken. So you have this simultaneous process where the OH approaches the carbon, the hydrogens shift in this direction, and then the bromine shifts again in that direction. So you have multiple motions of the atoms. You can imagine sort of like each atom has this x and y and z coordinates. So for n atoms, you have n sets of x and y and z coordinates, and they all move simultaneously as this reaction happens. And that is what this axis represents. That is what the x-axis in this reaction diagram represents, the collective motion of the nuclei in the atom as a reaction proceeds. And at any given point in this axis is one set of xyz coordinates of each atom. It's sort of static, it's sort of frozen in space at that point. And then the graph represents what is the energy of the system, of the entire system of the reaction at that point. Like I mentioned earlier, these are the reactants, this is the product, and this right here, that's known as the transition state, and that is also this energy right here. So the difference between the reactants and this highest point is the activation energy. To make the reaction happen, we have to supply enough energy to the system to bypass that activation energy. Usually it's heat, but it can be a number of things. And there's also ways to maybe lower that energy, so you can supply less heat to the reaction. It is important for the reaction to happen, you must bypass the activation energy, and that's kind of the point of what these reaction diagrams represent. So the reaction that we're interested in the case of the teeth whitening kit, the hydrogen peroxide breakdown, well, what happens to hydrogen peroxide is it eventually produces water and oxygen, but that is a multi-step process. The first step, the one that I want to talk about, is going from a reaction going from hydrogen peroxide to 2-hydroxyl. These are technically radicals, they have no charge. And the reaction coordinate looks something like this, which is a bit different than the example that I said, but it still has more or less the same feature. So we have the energy of the reactant, which is a nice minimum right here, and then there is a rise in energy. You can think of that as the activation energy, and then we get to the product side. So we must supply the reaction enough energy to somehow get over this hill and get to this side. So how does that happen? Well, it's a little bit interesting because there's no heat, or just arguably there's not enough heat that you supply. The reaction happens in your mouth, right? It's unlikely that there is enough heat there for the reaction to bypass this activation energy. More than that, the reaction happens in room temperature. Hydrogen peroxide is in cleaning products. So where does hydrogen peroxide find the energy to bypass the activation energy? Not to give it all away, but the energy comes from light. If it's not heat that is supplying energy to this reaction, it must be light, and that's indeed what happens. So how does hydrogen peroxide get the light? How does the light energy get harvested in order to bypass this barrier and produce the reactants that we're interested in? To answer that question, we have to talk about quantum mechanics. There's no way around it. Atoms and molecules are quantum mechanical objects. To understand them, we have to treat them as quantum mechanical objects. Very often in chemistry, you can sort of make do without worrying too much about quantum mechanics, but in this instance, you kind of have no choice. So how is hydrogen peroxide absorbing the energy? And there's a few other questions that we can answer with quantum mechanics as well, and with the topic of this video. Well, what is this line? Where do these energies come from in the first place? Where, why is it a line? Why is the energy dependent on this x-axis, on the nuclear coordinates? Well, where does that come from? How do we calculate it? And then how do we get light energy into this? So all of those questions, we kind of have to talk about the Schrodinger equation. Consider that we have something like a collection of point particles. They can be charged particles, it doesn't matter. And all these particles have positions, and they also have momentum. How do we get the total energy of the system? Well, we have to solve the Schrodinger equation, which sort of takes this form, where we have a Hamiltonian which operates on the wave function, and that gives the energy also times the wave function. And this is what is known as an eigenfunction equation. The way we solve this, well, we know the Hamiltonian, and then we have to find a function, which is the wave function, and an energy that satisfies this relationship. What is a Hamiltonian in this case? It's kind of an important part. It's technically an operator. We don't worry too much about that. You can think of an operator as something that operates on a function. In particular, in the context of the Schrödinger equation, it represents the total energy of the system. It represents the kinetic energy and the potential energy. In quantum mechanics, all physical observables are expressed through an operator. Momentum has an operator, position has an operator, the dipole moment has an operator, magnetic moment. Pretty much every physical observable is expressed through the operator, and the operator that expresses the total energy of the system is a bit special, and we use that in this equation to find the wave function and the energy of the system. As expressed, the wave function is a function, and while we can express it in different ways, it's usually a function that depends on the position of each particle that we are interested in. The energy, on the other hand, is just a number, or otherwise known as a scalar. And the one interesting thing about the Schrödinger equation is that there are infinite solutions. They are discrete, infinite solution, meaning that we don't just get one energy and one wave function, we get an infinite number of them. The one with the lowest energy, the lowest value of this energy number, is what's known as the ground state. And everything after that, they are excited states. Usually we mostly care about the ground state, but not always. So hopefully it's all clear so far. Let's move on to the next step. So now, instead of considering a random system of particles, let's consider an actual physical thing, an atom. And an atom is usually expressed with a nucleus at the center, which is positive charge, because only the protons inside the atoms have charge. The neutrons don't carry charge. And for the purposes of atoms and molecules, we don't really care what's inside a nucleus. We only care the fact that a nucleus is one charged particle, and in fact we treat it as a point particle. It has mass, but it doesn't really have size. And the same thing with the electrons, that are kind of, we can think of them as surrounding the nucleus. And now we have to solve, again, the equation looks exactly the same, and we have to solve this eigenvalue equations where we have the Hamiltonian, which represents the total energy of the system, or in this case, the total energy of the atom, and we have to get the different energies of the atom, the ground state of the atom and the excited state of the atom. Well, there are a few things that we kind of have to be careful about how we approach this. Well, we said that the Hamiltonian is the total energy of the system. That means it has kinetic energy and the potential energy. When we deal with the kinetic energy, it usually just depends on the particle itself. That means that the kinetic energy only depends on the momentum of that particle, and it's sort of independent of other particles, at least when we look at the Hamiltonian. That is, this electron has kinetic energy, this electron has kinetic energy, this electron has kinetic energy, and then the nucleus has kinetic energy. Because this is an atom and there's only one nucleus, we can always center our frame of reference, our coordinate system, on the nucleus, so that we don't really have to worry about the kinetic energy of the nucleus. In simple terms, however the particles in the atom move, we can always assume the origin is on the nucleus, so we don't have to worry about that. We kind of have to worry only about the kinetic energy of the electrons, at least as far as our purposes are concerned. And then the other half of the Hamiltonian is the potential energy, where the potential energy does contain the interactions between the particles. That means it contains the repulsive interactions between the electrons, and it contains the attractive interactions between the electrons and the nucleus. And the Hamiltonian must contain all of those pairwise interactions. So I'm not going to bother with what exactly that looks mathematically. You just have to know that it contains all of those. The electron and the nuclear attraction is not a big deal. The electron-electron repulsion, that complicates life a lot. That is what is known as a many-body problem when you have more than one electron. So, and we can't solve it exactly. In fact, we can only solve this equation exactly for the hydrogen atom. Anything else, we have to use approximations. We have good approximations, so that's not a big deal. But of course, the better the approximation, the more difficult it is to actually do it, the more computationally expensive. So we know what the Hamiltonian looks like. We can solve this equation, whether exactly or approximate, it doesn't matter, but we can obtain wave function, and we can obtain energies for the ground state and the excited states, and then we can write those down. And for each atom, we know what the ground states and what the excited states are. Again, the energies are just numbers. The wave function depends on all the coordinates of each particle of our system, but the energy is just a number, and that's important to remember. That's how we deal with an atom, but we don't really care about atoms that much in chemistry. Well, not in this case anyway. We want to upgrade to molecules. So let's look what this would be for a molecule. So we have a molecule here, and in principle, everything works the same as it does in an atom. There's no reason not to. We have the Hamiltonian, we have the same Schrödinger equation, we have the Hamiltonian, we have the wave function, but we have more particles, and we also have more types of interactions. Well, the one thing that sort of like the major thing that changes is now that because we have at least two nuclei, you cannot have, the smallest molecule that you can have is with two atoms. That means with two nuclei. The electrons, that you can have multiple around the nuclei. That doesn't matter for now, but we have two nuclei. That means that we cannot ignore the motion of the nuclei anymore. We cannot just put the origin of the coordinate on one nucleus, because then you have the other nucleus, right? So whether you want it or not, you kind of have to deal with the nuclear position. So that means that in addition to all the interaction that we had before, in addition to the kinetic energy of the electrons, in addition to the electron repulsion and the electron nuclear attraction, we have two new interactions. Now we have to deal with the kinetic energy of the nuclei, because again, we cannot assume that it's at the origin again. And we also have to deal with the nuclear repulsion. Well, solving the Schrödinger equation with electron repulsion is very complicated. Again, we cannot do it exactly. Now adding nuclear repulsion to that makes it even more complicated. Now we also have to worry about the kinetic energy of a nucleus. So that becomes complicated, that becomes difficult. So we kind of have to introduce more approximations into the mix. But before we do that, let's take a look one more time at our reaction coordinate. We express the energy of a reaction as a function of nuclear coordinates, and the y-axis is the energy, sort of. But here, in every example of the Schrödinger equation, we have said that the energy is just a number. It doesn't depend on anything. It's a scalar. So what connects these two, right? How can we get an energy that is dependent on the nuclear coordinates? And the answer to that is, of course, the Born-Oppenheimer approximation. That was in the title of the video. That's what I was trying to get to all the time. We got there. So, okay, let's now explain what that is. Something that Oppenheimer came up with in 1927 when he was a grad student of Max Born, hence the name Born-Oppenheimer. It's a very important approximation in quantum mechanics, a very important result of quantum mechanics. And I believe it's even briefly mentioned in the Oppenheimer movie. If it is, I'll put a brief clip because I'm pretty sure it is.
Oppenheimer. I caught your lecture on molecules. Oppenheimer, yes. I liked your paper on molecules. Probably because you inspired it.
But anyway, in my opinion, it's the most important thing that Oppenheimer ever did in his scientific career. Maybe others will disagree, but I think it's nevertheless pretty important. The math and physics of it can get a little bit complicated, and it's not really particularly important for what I'm talking about here. But the essential premise of it is, while we assumed our nuclei and our electrons are point particles, they still have mass. And the reality is that nuclei are considerably heavier than electrons, much, much heavier, like thousands of times heavier. So for the purposes of solving the Schrödinger equation in systems that we care about, we can just assume that the nuclei don't really move much. We can just assume that mostly the nuclei stay put, they stay as they are, and it is the electrons that move. So that effectively means, instead of writing one wave function, we can simply write our wave function as a product of an electronic wave function and a product of a nuclear wave function, which looks something like this. So instead of a total wave function that depends on both nuclear coordinates and electronic coordinates, and generally the way we do this is we write the electronic coordinates with a small r and the nuclear coordinates with a big R, we kind of separate it as a product of, we have one wave function that is an electronic wave function, and then one wave function that is a nuclear wave function. And in the electronic wave function, we have put the nuclear coordinates after a semicolon. That simply indicates that the nuclear coordinates are fixed, that this wave function represents the solution of the Schrodinger equation for this fixed set of nuclear coordinates. And that's very important, because that ends up simplifying a lot of things for us. And now when we solve the Schrodinger equation, we can just solve the electronic portion of the Schrodinger equation. We have again the same terms as before, nothing's changed. We have the kinetic energy, we have the potential energy, all the interactions, but we don't have to worry about the kinetic energy of the nuclei, because we've just assumed that the nuclei don't really move much, and that assumption is true a lot of the times. And when we solve this, we solve them for a fixed set of nuclei. That means that our energy is now dependent on that fixed set of nuclei. That is, we don't just have a number, we have an energy for a given position of the nuclei. The nuclei are frozen, they don't move, but the energy is dependent on them. And that's how we're able to get sort of a graph of an energy that is dependent on the position of the atoms at any given point. So basically what the Born-Oppenheimer approximation does, it separates the nuclei, the motion of the nuclei from the motion of the electron, and we solve a separate Schrodinger equation for each part. The one that we mostly care about is the one about the electrons, where the kinetic energy of the nucleus is 0. Again, we assume that the nucleus doesn't move. Of course, we can, if we're interested in the nuclei, for whatever reason, if we're interested in looking at the nuclei in more detail in a way that the nuclei move, we can go back and solve the other half of this separation. We can solve a Schrodinger equation for the nuclei, and in fact that gives us vibrational energy and that gives us rotational energy of the atom, which are a much smaller scale than the electronic energy. But in general, the first step is always to solve the electronic Schrodinger equation to obtain kind of the electronic energy, and that's generally what the energy that we care about when we look into chemical reactions. And of course, the important part is that now the energy is not just a scalar, the energy depends on the nuclear coordinates, and therefore we can plot the energy dependent on the nuclear coordinates. The Born-Oppenheimer approximation is what we call a semi-classical approximation. That is, if we are solving the Schrodinger equation for the electronic part, and we're assuming that the nuclei don't move, that means that the nuclei are effectively treated classically. We treat the nuclei as classical particles. Of course, if the nuclei don't move, that means we know their position and their momentum, which would violate the uncertainty principle. It's an important thing to keep in mind, but it's normally okay. And then the same thing would be on the other half. If we solve for the nuclear Schrodinger equation, we kind of assume that the electrons or the electronic density or the energy is static. So it's kind of semi-classical in both ways. And the justification or the motivation for this is, there are many. Of course, it kind of makes sense mathematically when we solve complicated differential equations like the Schrodinger equation. We like to separate our functions, we like to separate our variables, and if it makes sense, we also like to separate our particles. It makes sense from a chemistry point of view, even before quantum mechanics. We like to think we like to do chemistry by treating the atoms classically. That's kind of makes sense, has always made sense, even though quantum mechanics is essential in understanding chemistry. It kind of makes sense to treat the position of the atoms as something that you can think of classically. I don't know if that was an explicit motivation for Oppenheimer at the time, but it sort of, in retrospect, it's a way that we, at least people who do chemistry or who deal with molecules, it's a way that we do like to think about the nuclei portion of the atoms. The electrons are important, they form all the bonds, they make all the interaction, so we want to make sure those are treated quantum mechanically. But the nuclei, they can be static, they don't have to move at the same time. We can just assume that they behave classically, and that's perfectly fine. There's also sort of experimental motivation, which I'm sure it was known at the time, and that was how different in scale the electronic energy is from the vibrational energy, from the rotational energy. Was the electronic energy being sort of like accounting for the motion of the electron, sort of and the vibrational or rotational energy accounting for the motion of the nuclei. And here, of course, we're talking about in spectroscopic terms. When we measure these things experimentally, we're not really measuring absolute energies, we're measuring excitations or energy difference between different states. We're going to get to that in a little bit. But when we measure electronic excitations versus vibrational excitations or rotational excitations, the scale of those is very different. Electronic energies are much, much larger than nuclear energies. So that is a justification, motivation, I'm not sure what the right word is, but it sort of like helps understand kind of physically what the Born-Oppenheimer approximation, which is a mathematical approximation, what it describes. Because of the Born-Oppenheimer approximation, we're able to do these quantum mechanical computations on, molecules, not atoms, but molecules, materials. It's essentially in pretty much all research that involves these kind of calculations, whether it is in material discovery, drug development, etc. So it is very, very important. That's why I said I think it is one of the most, maybe the most important contribution he has done, because without that, pretty much the entire field of quantum chemistry would not exist in the way that exists today. Of course, you could say someone else would have figured it out. It would have been called whatever the name of that person is, but he did it. So that's what we call it today. Okay, so let's summarize where we are. We solve the Schrodinger equation to get the quantum mechanical energy, and the way we do this in molecules, which is what we're really interested in, is by treating electrons explicitly and then treating nuclei as static. So specifically, we have a set of coordinates for the nuclei. The electrons are so small that it doesn't matter. But we have a set of coordinates for the nuclei, a set of XYZ coordinates, which again, in our particular case, we express them in this x-axis here, and then we compute the energy at that set of coordinates, at those set of coordinates. What that means is we solve the Schrodinger equation for those set, and we obtain energy right here. Then we have another set of coordinates, and we solve and obtain the energy over here. Then we have another set of coordinates in here, and that's how we generate sort of graphs like these kind of like potential energy surfaces, which sort of rely on the Born-Oppenheimer approximation. In fact, these are also called sometimes Born-Oppenheimer surfaces. I am simplifying a little bit here because technically this is not just the electronic energy. This contains some other stuff. This is when you see graphs like these are technically represent what is known as the total free energy, which contains, which also may contain also some nuclear contribution. It also may contain some statistical effects, some thermal effects, etc. But roughly speaking, we can just ignore all those and say this is just the electronic energy, and that's usually still gets the point across. But anyway, the fact that we can have this a graph like this, is because we can compute the energy at different nuclear geometries, which, like we said many times, they're represented on this axis here. So we have a surface, a line like this. The other thing to point out, which may also be intuitive at this point, generally, if we have a surface like this, atoms and molecules want to be at the lowest energy configuration. So if you, let's say, start over here, you are at this geometry, the molecule will want to go down to this point here, the minimum configuration. That is also known as the equilibrium geometry of the molecule. You can think of it as a ball rolling down a hill. If you start at a point where there is a non-zero slope at that hill, the ball roll down all the way to the valley where it can just sit happy at the bottom of the hill. And that's what molecules do as well. If you start at a high energy geometry, it will go down. If you start on this side, it will go down this here, and it will happy just sit around here. It will vibrate, but that's fine. We don't care about that. So that's why when you have a reaction where you have this kind of hill, you have to supply energy to the reaction in order to make it go up the hill and up all over to the other side. So hopefully that made a little bit of sense. So now that we have some of that basic science down, let's go back to our example, the example that we really care about. What happens to hydrogen peroxide in this case? So we said that the Schrodinger equation gives us multiple energies. It doesn't just give us one energy. It gives us the lowest energy, which is the ground state. And that's what's usually is depicted here. When you see diagrams like this, they usually show the ground state. But we can also compute higher state, right? We can compute excited states, that is energies that are larger than the lowest energy, which is the ground state. And within the Born-Oppenheimer approximations, those excited states behave exactly the same as the ground state. That means they depend on nuclear coordinates, and you can plot them along the same axis just like as you plot the ground state. To give a quick example, if we have some kind of molecule that is in the ground state right here, if we excite it by absorbing light, of course, that's how you excite molecules, it goes straight up. If we draw essentially a vertical line from the minimum, because again, in any given surface, the molecule wants to be at that minimum. Wherever you start, it wants to roll down the hill to that minimum. So it will be here initially, and if it gets excited, it starts here. But again, the excited state surface behaves like the ground state surface, more or less. So now that it's here, it will want to roll back down to this minimum and be here. Of course, now they're not exactly the same. Excited states of atoms, molecules, or generally any quantum mechanical system, they are inherently unstable. So it might sit here for a little bit after it's absorbed light, but then it will fall back down and it will radiate light, which is proportional to the energy difference between this point right here and this point right here. And that's how the molecule goes back to the ground state. And we call that process fluorescence, because the light that it radiates will be a different wavelength than the light that it absorbed to get up to the excited state. So again, we said it goes to the excited state minimum, the minimum of the surface. Eventually, it goes back down after some time. It's relatively quickly, but it can be a while, in fractions of a second usually. And then now it's here, but now again, it's at a higher energy geometry. It will roll back down to the minimum, and that's essentially that. And it's back where it started. You can absorb light again, doesn't matter, but we are here, and that's how excited states of molecules usually work. We said that we excite a molecule, or even an atom, but in case we're dealing with a molecule, by absorbing light, and the energy of light that it needs to absorb, it is usually the difference in energy between these 2 points. And the y-axis is the energy. And because we measure the energy, or we express the energy of light by wavelength, if you've somehow calculated this energy difference and you know the energy, you can convert that into wavelength, and you'll know what wavelength of light this molecule absorbed. Or conversely, if you've done the experiment and you know the wavelength of light that it is absorbed by the molecule, then you'll know the energy of the excited state, the excitation energy, and then you can make predictions, or you can do calculations and see if those calculations match experiments. So that's how that works. Okay, so what has this all led up to? We know where the energy comes from. Quantum mechanical calculations, the Schrodinger equations. We know where the line comes from, where the surfaces come from. Again, it could be a two-dimensional line or one-dimensional like it is here, but it could also be multi-dimensional, a surface. That's why I kind of keep calling it surface without explaining it, but that's okay. But we know where those come from. It's the Born-Oppenheimer approximation. So that's kind of the second piece of the puzzle. And we also know how these molecules interact with light by absorbing it, a higher energy state, which is an excited state. And that is also a Born-Oppenheimer surface that behaves the same. It may have a different minimum. So again, molecules want to roll down the hill and go to the minimum. And if it's an excited state, it will go back down to the ground state somehow. But we're not there yet. So we have all the pieces of the puzzle. How does that involve hydrogen peroxide? How does hydrogen peroxide break down into two hydroxyl radicals, which is what the reaction that we've been trying to describe this whole time, where we know that it somehow absorbs light. So we have to know what the potential energy surface, what the Born-Oppenheimer surface is, not in the ground state, because we know the ground state, but what is in the excited state. And if you either look it up or you do the calculation, you plot it, I'll post the paper that I got this from on the description, but it looks something like this. And that's, I think, quite revealing, because we can now repeat the same process that we saw in this example molecule from the ground state of the hydrogen peroxide. We have the vertical excitation. That means, initially the molecule will sit here, happy, vibrating in the equilibrium geometry, and then it absorbs light. We know from calculation experiment that this light is in the UV range. I don't remember exactly what the wavelength is, but it's somewhere in the UV, and we know that UV is usually available from sunlight. Anyway, so again, I get excited here, but of course, now it's in a non-minimum portion of this surface. Of course, this excited surface doesn't have a minimum, so the molecule, again, think of the ball on a hill metaphor, would just simply roll down all the way to this portion of the surface where, well, we are already here in the geometry where we want to, again, because that's kind of what happened in the excited state. And also another thing that happens is that now the energies of these are the same. So that means that the molecule can just go back to the ground state without releasing a photon. This happens very fast. It's known as radiationless decay, because there's no energy difference. The energies are identical, so it doesn't need to emit a photon to go back to the ground state. So we started with a geometry here, and our goal was to move over here. Well, we took you can think of it as sort of a shortcut. We went up here, then we rolled all the way down here, which is where we wanted to be, and then we generated 2 hydroxyl radicals, which is what our goal was this whole time. Of course, this technically can collide with other hydroxyls and go back here, because this is not exactly a minimum, but hydroxyl is so reactive that it will interact with anything else that it sees, and if it's likely that it will see another hydrogen peroxide, it will sort of like initiate a chain reaction type of deal that will end up with mostly water and oxygen. But that's besides the point. We only cared about this first step for what we wanted to show. And the way that this happens is, it's kind of fascinating how a molecule is able to harvest light in order to bypass kind of like the activation energy of a process that we kind of intended to happen. It's almost like you're trying to get at the top of a hill. Again, going back to the hill metaphor, instead of walking up the hill the conventional way, you take a helicopter straight up and then you kind of glide towards the top of the hill. And this is exactly what has happened here. Of course, as an interesting side note, we're sort of like, we're explaining all this through the lens of the Born-Oppenheimer approximation, through these things that we've sort of called Born-Oppenheimer surfaces. A fun fact, or an interesting fact about the Born-Oppenheimer approximation, is that in these areas where the energies of the two states are close or even identical, the Born-Oppenheimer approximation kind of breaks down. It's kind of not valid anymore. I mean, it's valid enough that we can sort of follow this explanation, and it's good enough to make prediction, but it doesn't hold rigorously as well as it holds in these areas where the states are well separated. And I'm not going to go into the details as to what that is, but kind of recall what we said up here, that the assumption, or part of the justification for the Born-Oppenheimer approximation, is that the energies of the nuclear motion and the electronic motion are well separated. That means that the difference in electronic energy and the difference in nuclear energy are at a different scale. But when you're here, where the difference in electronic energies are so small and even identical at some point, this assumption no longer holds true, and therefore the Born-Oppenheimer approximation no longer holds true. At least not exactly. You might have to add corrections, and you might have to make modification, and dealing with those cases is very, very difficult. It's an area of active research, and we won't talk about it any more than that. Still, it doesn't really prevent us from understanding how these type of reactions happen. And again, to kind of repeat the point that I made earlier, this is only the first step in a multi-step reaction. This is just how we generate the hydroxyl radicals, which will then go into to interact with more peroxide, which initiates a chain reaction, and which eventually ends up with water and oxygen. And I believe this is the reason why originally hydrogen peroxide used to be called oxygenated water, because when exposed to sunlight in the environment, it ends up just producing oxygen and water. That's also why they say that's why you are supposed to store peroxide in opaque containers that are not usually exposed to sunlight, because it will decompose otherwise. I hope you enjoyed this explanation. I hope you enjoyed the part of how light is enabling a chemical reaction that otherwise would require a lot of energy, or a substantial amount of energy to happen. And this, I find this area of chemistry, physical chemistry very fascinating. That is, reactions that are enabled or that are powered by light. And because they pop up in very interesting places. One other example that I think it's interesting to mention is the mutation of DNA on our skin from sunlight, under sunlight, which, of course, as we know, can lead to cancer. This is another type of reaction that happens through an excited state. In this case, this is a reaction that we don't want to happen when exposed to sunlight. So we can kind of understand this again by drawing the diagram of what this reaction sort of looks like. Again, this is an approximation. I didn't look up the exact details, but here we have sort of like the DNA base. Specifically, I believe it's a derivative of cytosine, which is, normally it performs its function, is in your DNA. It forms base pairs with whatever cytosine forms base pair. Is it thymine? I don't know. Anyway, and it's here, and this is where it functions normally. And if it gets enough energy, it forms a modified version of that we don't want. This is bad, and this can lead to skin cancer. And of course, normally there's not enough energy in your body for this to happen. However, when exposed to sunlight, if this gets excited to something that looks like this, approximately, not exactly, but something like this. So when it gets excited, it can end up in this excited state that when it relaxes can fall right here or approximately there. And what's interesting is that, this doesn't necessarily mean bad news. Evolution has chosen very well, in that what happens is very often this will just fall back right into here, and that's good. But if this happens enough times or with enough intensity, it can somehow this go over here, and this is bad. This leads to cancer, and as far as we know, cancer is bad. So, make sure you wear enough sunscreen so that this doesn't happen, or it doesn't happen too often, so that it statistically leads to cancer. I think that's how everything works. Okay, that's all I wanted to talk about. I think it got a little bit more complicated than I initially intended. But anyway, I enjoyed talking about it nevertheless. If you are completely confused and you have any questions, feel free to leave them in the comments. If you enjoyed the video, consider leaving a like or subscribing. Otherwise, I will see you next time.